Welcome to this tutorial about power-efficient neural networks using low-precision data types and quantization. For material like this video, slides and code, follow the URL or QR code. So this talk is part of a series of talks. After giving the opening remarks, I will talk about low-precision data types. This lies the foundation for session 2, in which Marcus will talk about the fundamentals of quantization algorithms, and session 3, in which Timon will talk about advanced quantization methods. But why are we interested in power-efficient neural networks? Usually the system and energy costs of neural networks are pretty high. Reducing these costs enables new edge applications like autonomous driving or AI on wearables. Reducing these costs also speeds up the development cycles. This means we can train faster and longer. Reducing these costs enables real-time applications. Nowadays, we are already used to interaction via text and voice, and real-time interaction via video is in the making. Just imagine that we can provide a personalized AI teacher to all the underprivileged children. However, this would require 100 times the global electricity consumption as of now. Certainly, this challenge requires innovation, not only in terms of models and algorithms, but also in the execution of the models on hardware. But why are the models so power hungry? This is pretty easy. We are in the age of scaling laws. This means we make the models bigger, train them longer, and iterate more often over these models during the inference phase to get more intelligent systems out of it. So let's start with the model size. Bigger models require more data storage and more data transfer. Here the number of parameters is plotted across the publication date, across multiple modalities. The dashed line shows the number of parameters doubles every year. But models are not only bigger, they are also executed more often. This is shown on the following slide. Long story short, the more compute you invest, the more intelligent system you get out of it. Previously, we talked about a scaling law. In fact, it's not only a single, but a combination of 3 scaling laws that are stacking. There's the pre-training scaling. This means we train the foundation models on a lot of data, and we increase the number of training iterations. There's post-training scaling, which means we fine-tune the foundation model to our target domain. And there's test time scaling, where we iterate over the model for long thinking or reasoning. In summary, intelligent system requires a lot of compute, both in training and inference. And the more compute is required, the more hardware is required, and the higher is the power consumption. This is depicted on the left-hand side, where the global power consumption of data centers is plotted across time. During the last 8 years, this power consumption tripled. This power consumption is also expected to further grow, which is shown on the right-hand side, this time for the US only. Within the next 5 years, the power consumption is expected to more than double. And this is not only in absolute terms. Also, the share of the total US power consumption is expected to significantly increase. However, the power availability is limited. Power availability is not only an infrastructural challenge, but also a societal one, especially in the context of global warming. Certainly, there is a big environmental impact of AI, especially due to its power consumption. I want to give you 2 examples that show this. So recently, big tech announced that they want to reactivate nuclear power plants, and they're even planning to build new ones. And quite surprisingly, currently there's a shortage on natural gas turbines because big tech is building gas power plants next to their data centers. This is quite a motivation to reduce the power consumption. And the most effective way to do that is low precision data types. This is part 1, low precision data types and computation. So I asked a chatbot to summarize my talk, and it came up with the slogan, less bits, log math, more compute. My name is Thomas Pfeil. I hold a PhD in physics, and I previously worked at IBM and Bosch Research. Currently, I'm leading the hardware algorithm co-design team at Recognize. Let's first have a look at the overview of methods for network compression. Of course, there's quantization, which means reducing the bit width of data types. Then there's pruning and sparsity, which means removing parameters and activations. There's low-rank approximations, which means projecting the feature space to lower dimensions. Then there's knowledge distillation, where we use the output of a teacher network to train more efficient student networks. And then there's neural architecture search, which means optimizing the type and numbers of layers in a neural network. Today we will focus on quantization because in terms of power consumption, this is the most effective method. At the live talk, I conducted a poll to see what is the expert level of the audience. And the outcome was that most of the audience already executed neural networks with 8-bit and 16-bit precision. Some of them executed networks with 8-bit precision and less, or quantized neural networks themselves using off-the-shelf toolboxes. And very few people of the audience wrote their custom quantizers or even modified the definition of basic operations like multiplication and addition. Today we will focus on the last 2 points, so this is rather the expert level. And now you might have noticed why I'm talking about multiplication and addition. So what compute actually dominates in the execution of neural networks? These are dot products. Dot products are the workhorse of AI. They are used in matrix multiplications. If you want to multiply matrix A with matrix B, then the elements of the resulting matrix C are the sum of the products across index K. However, dot products are not only used in matrix multiplications, but also in normalization layers, like for example here in RMS norm. Note that dot products are used both in training and inference. However, the requirements for dynamic range and precision might be different in training. So dynamic range means the ratio between largest and smallest representable value, and precision is the smallest difference between values. Also, the parameters and activations might have different importance. So this means they differently contribute to the output of the network. The last 2 points will be addressed by the other sessions. So now let's have a look at the cost of dot products. You have to store your vector A and B in memory and transfer them to the compute engine in Cray, where the multiplication and addition happens. The result is then transferred back to memory. So let's first have a look at the requirements for storage and bandwidth. So this pyramid shows the typical memory hierarchy in hardware. The broader the segments, the larger the storage, the lower the cost, but also the slower the access. And if you go up in the pyramid, the cost increases, the size decreases, but also the access is faster. So let me just give you some examples. If we start from the very top with the registers, this is the memory in the compute engines. Has typically a size of kilobytes and is very fast. Below, there's the SRAM. SRAM is usually used for caches or for shared memory, has a size of megabytes, but is still on chip. As chiplets, usually we use memories like DDR or HBM. HBM is high bandwidth memory, and DDR is a special kind of DRAM. Both kinds of memory have usually a size of gigabytes and are known as the main memory of GPUs as you use them. And below is memory like solid state or hard drive disks. This is where you store your training data or databases. So let me give you some best practices how to use hardware systems with such a memory hierarchy. So the golden rule is to keep data local and to reuse local data. Also use hardware with a lot of fast memory, right? So I addressed it before. The larger your main memory, HBM or DDR is, the larger models you can deploy. And also use the fastest memory for the most frequently used data. This is not only to reduce the latency, but also to reduce the power consumption. The faster the memory, the lower the power consumption. Let's, for example, compare the power consumption of SRAM compared to DDR. So SRAM requires 100 times less power. Now let's have a look how a linear layer is executed in such a memory hierarchy. So usually the outputs of a linear layer are kept local and the input activations and parameters are kept in SRAM and or HBM. Overall, the size of fast memory determines the size of models that you can deploy. So how can we mitigate that challenge? A way to reduce the storage is quantization. But there are different types of quantization. There's quantization to low precision data types. So here I depicted on the example of floating point data types some examples. The industry standard of general purpose compute, for example, is floating point 32. For AI applications, the standard is FP16 or variants of it. Usually this is then called mixed precision training and inference. Why mixed precision? So for weights and activations, 16-bit data types are used. But for intermediate results like partial sums and matrix multiplication or normalization layers, usually higher precision is required. Then there's a new emerging standard in terms of data types, which is FP8. So more and more models are deployed in FP8, like for example the DeepSeek model. And then there are experimental data types like FP4. Alternatively, you can also use codebook quantization. So what does this mean? This means, for example, here we have a matrix and we cluster the entries of the matrix. And then instead of storing the full precision weights, we only have to store the cluster indices. And together with the also stored centroids, we can reconstruct the original matrix. This is scalar codebook quantization, but we can also apply the same technique to vectors, which is depicted below. So here on the example of convolutional filters. So convolutional filters are shown across output and input channels, and the cluster index is highlighted with different colors. For example, here the red filter shows up in two different output channels. So instead of storing the filters, we only have to store the indices for these filters. After discussing the requirements for storage and bandwidth, let's have a look at the cost of arithmetic operations. The table on the left-hand side shows the energy cost for addition and multiplication for integer and floating point data types across different bit width. In general, multiplications are more costly than addition. And as reference, a multiply accumulate using floating point 32 data types requires approximately as much energy as reading from SRAM. Reading from DRAM requires over 100 times more energy. Also note that multiplication scales quadratically with the bit width, while addition scales linearly. To give you an example, an 8-bit integer addition requires 0.03 picojoule. If we multiply that by 4, we approximately end up at 0.1 picojoule, as required for a 32-bit integer addition. For multiplication, an 8-bit integer multiplication requires 0.2 picojoule. If we multiply that now by 16, because it scales quadratically, we end up with approximately 0.1 picojoule, as required for a 32-bit integer multiplication. But what does this mean on system level? On system level, the lower the precision, the more operations we can fit onto a single chip. And the more operations we can fit onto a single chip, the less chips we have to interconnect. And this is pretty good news because usually the interconnect between chips is the bottleneck in deployments. Let's now compare the cost of multiplications to additions on the examples of integer 32. Multiplications require more than 30 times more energy than additions. So it would be pretty awesome to get rid of these multiplications. There are different ways to do that, and today I want to highlight one specific way, and this is logarithmic math. Using logarithmic math, multiplications in linear space become additions in logarithmic space, as depicted by the two equations on the left-hand side. However, accumulating these products is rather expensive in logarithmic space, so we have to go back to linear space to do that. Overall, this means, although we have replaced multiplications by additions, we have to execute logarithmic and power functions to switch between linear and logarithmic space. These functions are rather expensive to implement on hardware, and this is why we are using an approximation for these conversions between linear and logarithmic space. These approximations are called Mitchell approximation. And when we go from linear to logarithmic space, we can just interpret the exponent and mantissa bits of floating point numbers as integer and fraction bit of logarithmic numbers. And if we go from logarithmic to linear space, we can apply the same methodology and interpret the integer and fraction bits of logarithmic numbers as exponent and mantissa bits in floating point numbers. This was pretty fast, but we will dive into the details later on. After also having discussed the cost of arithmetic operations, let's put it all together again. There are three different ways for inference. There's full precision inference, where high precision weights and activations are loaded from memory, and all operations are executed in high precisions. The results are also written back in high precision. Then there's simulated quantization. Low precision weights and activations are dequantized in or close to the compute engine. However, multiplication and addition is performed in high precision. The result is requantized to a low precision data type before writing back to memory. Note that the codebook approaches that I mentioned before also use this scheme. Here, low precision indices of clusters are used to index the cluster centroids, and then these cluster centroids are used to perform multiplication and accumulation in high precision. The result is then clustered such that the indices are then written back to memory. Low precision inference, like shown on the right-hand side, is the most energy efficient way. Here, weights and activations are stored in low precision. Now, the multiplication is also performed in low precision, while accumulation stays in high precision. This is because the partial sum of dot products has potentially many terms. The result is again requantized back to a low precision data type to be stored in memory. This approach is especially energy efficient if the hardware system natively supports low precision multiplication. Now let's compare the different quantization methods. In terms of compressing weights and activations, the codebook approaches, so codebook quantization and vector quantization, are a bit better than low precision data types, so they just achieve higher compression ratios. However, when we look at the energy efficiency of computation, like we've seen on the previous slide, low precision data types excel. They are a lot more energy efficient. And the same applies to hardware friendliness. Codebook and vector quantization add additional complexity for supporting potentially a lot of lookup tables. Of course, we are interested in the most energy efficient solution. So the best trade-off here is low precision data types, and this is why we'll focus on this quantization approach today. Let's discuss data types in detail. There are two classes of data types, linear and nonlinear data types. Example for linear data types are unsigned integers, which are composed of integer bits, signed integers, and fixed point numbers, which are composed of integer and fraction bits. An example for nonlinear data types is the logarithmic number system. Here we put a fixed point number into the exponent of 2. Then there are also floating point numbers, a nonlinear data type, which is kind of a hybrid between a logarithmic data type and a fixed point number. So the exponent lives in logarithmic space and the mantissa in linear space. On this page, I depicted only 8-bit data types. And for FP8, I depicted two different configurations, one with 4 exponent and one with 5 exponent bits. But there are a lot more configurations used in AI. For integer data types, the industry standard is integer 32 with 1 sign bit and 31 integer bit. And then we can go down all the way to int4 with 1 sign bit and 3 integer bits. For floating point data types, it's a little bit more complicated. So here again, we start with the industry standard, floating point 32, 1 sign bit, 8 exponent bits, 23 mantissa bits. If we reduce the number of mantissa bits, we end up with TensorFloat 32. It's a little bit confusing, that's called 32, it has only 19 bits. If we further reduce the number of mantissa bits, we end up with BrainFloat 16. If we then decrease the number of exponent bits, we end up at floating point 16. And we can further decrease the exponent and mantissa bits and go all the way down to FP4. Now let's have a look how high precision data types are quantized to low precision. As an example, I want to showcase this on integer data types. At the very top, you can see a data distribution that we want to quantize to the target quantization grid as shown in green at the very bottom. So usually 2 steps are applied, scaling and shifting. In symmetric integer quantization, we take the max absolute value of our distribution, in our case 63.5, and scale it in such a way that it's then aligned with the max value of the quantization grid. For symmetric quantization, we do not apply shifting. Note that the scaling can be derived from two linear equations. If you look at the two bottom rows on the left-hand side, you will notice that some quantization levels of the quantization grid are not used. And to mitigate this shortcoming, let's have a look at asymmetric integer quantization. So here again, we start with the data distribution at the very top. And now we scale this distribution in such a way that it has the same range as the quantization grid. Afterwards, we shift the 0 point such that the distribution is perfectly aligned with the grid. Now we do not have unused quantization level anymore. However, we need to scale and shift. And it's not guaranteed that the 0 point is maintained. We can apply similar methods also to logarithmic and floating point data types. I won't dive into details here. If you're interested, just look up the references. And here for symmetric and asymmetric integer quantization, I've shown the max scaling method. So we use the absolute maximum or maximum values for the scaling, but there are also other choices for us that will be covered in the other sessions. And now the big question is, at what granularity are we quantizing? So we can do it at a granularity of a tensor, of a full tensor. This means all elements in the tensor share a single scaling factor or shift, also called 0 point. Alternatively, we could split up the tensors in multiple groups, like for example channels. Then each channel would have its individual scaling factor and 0 point. To drive this even further, we can also do blockwise quantization, where it's a fraction of a channel. Since blockwise quantization usually achieves the lowest quantization error, let's have a look in detail. Block quantization is defined as a block of elements yi. So it's k of these elements, the block size is k, and each of these elements has data type q and bit width n. All these elements share blockwise parameters, like the scale or the 0 point as introduced before. And these shared parameters also have a data type p and bit width m. So now I depicted all the three parameters in red. And as you may notice, there are a lot of combinations out of which you can build your block quantization data type. Let me give you some examples of block quantization. There's mxfp6. The block size is k, and this data type has a scale of data type E8M0. So this means 8 exponent bits. So it's 2 to the power of an integer. The elements are of data type fp6, and we can compute the effective bits per value by multiplying the block size with the number of bits for the elements plus the number of bits for the scaling factor. So here no 0 point is used. Then we end up with 6.25 bits per value. Another example is llama CPP. Here we use a block size of 32, scale and 0 point are of data type int6, the elements are of data type int4. The effective number of bits is 4.375. The interesting part here is that we can now use this block data type as elements for a superblock. In this example, a superblock consists of 8 blocks, and we share a common scaling and 0 point of data type fp16 for these 8 blocks. Then the effective bits per value compute as 4.5. Let's briefly discuss these microscaling data types like mxfp6, since these are an upcoming standard. The benefit of these microscaling data types is that they also simplify the computation of the dot product. Since the scaling factor are power of 2, their multiplication becomes an addition in log space. We already know that trick. And the dot product then becomes a dot product of the elements of the blocks A and B. Now let's dive into some hands-on coding session. This coding session will cover the introduction of data types, handling of outliers, and multiplierless dot products. If you want to follow along or even want to modify the code yourself and execute some stuff, gather some hands-on experience, I encourage you to follow the QR code or URL as listed on this slide. In my opinion, only if you touch it, you learned it. So please take this as an interactive session and try things out yourself. Let's jump into the coding session. Here I'm using a Marumo notebook that you can access via the URL that I shared at the beginning of this talk. Let's first talk about data types. On hardware, values are encoded as sequences of zeros and ones. So what does this mean for integer and fixed point data types? So let me scroll down. First we start with unsigned integers. Unfortunately, I promised my colleagues not to live code, but let me quickly remove some parts of the code for simplicity. All right. So for unsigned integer, all of these boxes are bits. So it's 8 of them. It's uint 8. And here at the very bottom, later on, we can select this sequence of bits and generate the values out of it. So the first thing that we do is we set the sign to be positive because it's an unsigned integer. Then we reverse the bits, the sequence of bits, because for data types, we read from right the least significant bit to left the most significant bit. We initialize the result to 0 and then we iterate over all these bits. And whenever a bit equals to 1, then we add to the result 2 to the power of the index of this bit. So if we look at the output below, I can give you an example. So least significant bit is 1. Corresponding value is 2 to the power of 0. Because the index is 0 for the least significant bit, this results in the 1. The second bit is a 1, so 2 to the power of 1 results in 2, and so on. So overall, the value represented by only ones is 255. So in the field of computer vision, you should be very familiar with this value. So now we can also select a random sequence of ones and zeros and generate the resulting value. Let's now have a look at signed integers. So signed integers have a sign bit. This means whenever the sign bit is 1, then we define the result to be negative. Everything else is like for unsigned integers. So let's also generate some examples. So here we have a leading 1, so it's negative. If we toggle this to a 0, we get a positive result. If we now set all bits to 0, we get a 0 out of it as expected. And if we now toggle the sign, we get a -0. So we spend 2 code points for representing the 0, and this is quite a waste. And also the reason why in practice not the sign magnitude representation is used, but the 2 complements representation. So what is the 2 complements representation? I haven't implemented it, but I can briefly showcase it on the example of unsigned integers. So in the 2 complements representation, the contribution of the most significant bit is negative. So in this example, it would mean it's a -128, and here the rest adds up to +127. So in total, this would be a -1. Okay. Next stop is fixed point numbers. Here we have 1 integer bit and 7 fraction bits. Here it's quite easy. We just subtract the number of fraction bits from the index. So here it's a -7. And this results in the following examples. So only the integer bit contribute to values that are larger or equal to 1, and all the other contributions accumulated are always smaller than 1. So here this would be the largest value. If I enter some random sequence, we see that we can represent different values with fraction. Now let's have a look at floating point data types. The sign is interpreted as for signed integers, and in the floating point data type we have also exponent bits and mantissa bits. So the exponent bits are here in the exponent of 2, and these exponent bits represent an integer, an unsigned integer. So the smallest value for this exponent is 0. So this would mean 2 to the power of 0 is 1. So this would mean the smallest value that I can represent is a 1. And this is of course very impractical, and this is why the so-called exponent bias was introduced. So the exponent bias is defined as an integer and as a max value of an integer, and this integer has 1 bit less than the exponent. So 1 bit less than the exponent, then it's in the exponent of 2 and -1 to get the max value of this integer with 3 bits. And this is 4 plus 2 plus 1, it's a 7. And by definition, the exponent bias is negative. The other part, the linear part, consists of a 1 plus a fixed point number with a fixed leading 0, and the fraction is defined as the mantissa bits. So now let's have a look at some examples. So first field is sign, here exponent bits, and here the mantissa bits. So my exponent bits represent a 15, my exponent's bias is -7, and my mantissa bits with the leading 0 represent a 0.875. So together these bits represent a value of 480. So now we can choose a lot smaller exponent. Now the exponent is 1, -7, the exponent bias. Now the result is smaller than 1, as intended. To further reduce the result, of course, we could also reduce the mantissa value. And of course, we can also toggle the sign. So let's toggle it back, and let's see what happens if I set the exponent and the mantissa to 0. Surprisingly, the result is not 0, but a positive value. Of course, not having a 0 is very unpractical. This is why usually this bit pattern, so all zeros, is defined to be 0. So this means the smallest value would then be a mantissa of 1. And the second smallest value would be here a 1, 0. If we now go back to a 1, we actually see that there is a big gap between this so-called smallest normal value and the 0. And to address this gap, what is usually used is so-called subnormal values. And for subnormal values, whenever the exponent is all zeros, then we replace this 1 by a 0. So we linear interpolate between 0 and the smallest normal code point. We do not consider this in the notebook here, We also do not consider the representation of 0, and we also exclude the consideration of special symbols like not a number and infinity. Now let's have a look at logarithmic numbers. So logarithmic numbers are pretty similar to floating point numbers. However, we do not have a mantissa, but instead we have a fixed point number in the exponent. And this fixed point number has integer and fraction bits. Like above, we also have an exponent bias. And if we look at the examples, so for all ones, we have an exponent of 15 plus the contribution from the fraction 0.875 minus the exponent bias, which is -7. And this results in a value as listed below. So again, we can just reduce the value for exponent and mantissa and generate all the code points of this data type. You may have wondered why I introduced this rather exotic data type over here. I did that because this data type becomes very handy in the context of logarithmic math. So I will show this later in this notebook. So now let's compare the quantization levels of these three different data types. So to this end, we get the representable values, so the quantization levels for these three different data types. So for LNS, we use a configuration of 4 integer and 3 fraction bits. For floating point, 4 exponent and 3 mantissa bits. And for the signed integer, we use 7 integer bits. This results in a distribution of quantization levels as depicted here. And to better compare them, we normalize these value ranges to 1. If we now zoom in to large values, we see that we have a lot more quantization levels for the integer data type compared to the two other data types. And if I zoom in to the small values, we see that we have less quantization levels for the integer data type compared to the two others. Also, we see for the floating point data type that for each exponent value, we have a regular pattern. So this means quantization levels that are equidistantly distributed. Whereas in the case of the logarithmic data type, the quantization levels are purely exponentially distributed. And now let's have a look at the errors of these different data types, so the quantization errors. So how do we quantize? Here I use a very simple technique, which is not very performant in practice. And in the simple technique, we just choose the quantization level that is closest to the original value, which can be seen here. Okay. So we quantize a range of values, we get the errors, we keep track of the max error, and then we plot the results for all three different data types. And this is what we get out of it. So here, the absolute error. Integers have the smallest absolute error, whereas for floating point and logarithmic data types, the absolute error grows with the value. So let's just scroll up again and let's reset the view. So for floating point and logarithmic data type, the distance between quantization levels is rather large for large values, and this explains why we also have a large absolute error here. If we now look at the relative error, we see that the relative error increases for small values for the integer data type. This can also be explained in this view above. let's reset it and let's now zoom into small values. Here we see that there are only very few quantization levels for the integer data type, which results in large relative errors. The relative error is rather small for floating point and logarithmic data types and is smallest for the logarithmic data type, because here we have this pure exponential distribution. So now let's normalize like above to 1. And let's also plot the values logarithmically. I think this plot describes it best. Floating point and LNS data types have the largest dynamic range, and the overall smallest relative error has the logarithmic data type. Tensors with outliers are pretty hard to quantize, and since they show up a lot in LLMs and generative vision models, we will address them here. So let's first start with an artificial data distribution. We draw numbers from a normal distribution, so here without outliers, and then we add a single outlier that is 30 times larger than a normal distribution, which you can see here on the very right-hand side. So now we quantize a tensor. More specifically, this tensor is a vector of size 128. First, we normalize this tensor. Then we quantize these normalized values. For this, we use the normalized quantization levels, as also shown above. And then we compute the reconstructed values. So this means we scale the quantized value with the scaling factor. We also keep track of the quantization levels. So here we show the quantized values across the original values and also the relative errors across the original values. For now, for a distribution without outliers. So we see that the relative error is rather low, except for some very small values. We already know why, because for small values, there are only few quantization levels, so there's a large relative error, comparably large. Now we can use a floating point data type instead of an integer data type, and we see that the relative error is a lot smaller. So here, let's just go back to integer and show you. So here the errors go up to 10 or 20. For floating point, the error is smaller than 5.5. If we go to the logarithmic data type, we see, as expected, that the max error is even smaller. Here we can also zoom in to small values and see that we have a lot of quantization levels. So the relative error for these is pretty small. Now we can reset the axis and switch to the distribution with the single outlier. Of course, now we want to represent these outliers or the single outlier, but for the logarithmic data type, this is no problem because we have a lot of quantization levels for small numbers, so the overall error stays very small. We observe the same for floating point data types. If we now go to the integer data type, we see that we also want to represent the outliers. Then there are many unused quantization levels. And for very small values, so if we zoom in to all the values except the outlier, we see that only a handful of quantization levels are left. And this results in rather large relative errors. So how can we address this? I already mentioned this in my main talk. We can address this by blockwise quantization. In blockwise quantization, we compute the scaling factor only for a subset of the values in the tensor, the so-called blocks. And this reduces the impact radius of outliers. So now let's also visualize this. First of all, here's a function to extract the blocks from the tensors. And now let me introduce two modes. So there's one mode where we first extract the blocks and then quantize them. And there's another mode where we first quantize the tensor and then extract the blocks. If we take a group size of 32 and look at the first block, we see that there's no difference between these two modes. If we go to the next plot, let me just turn off some visualizations. We see as reference the same visualization as we've seen before. So there's only few quantization levels left for small values and the relative error is rather high. But if we compute the scaling factor only for these values within the blocks, so the first mode, the block quantization mode, then we have a lot more quantization levels and our quantized values are pretty close to the unquantized ones and the relative error is rather small. This also applies to the other two remaining blocks. If we now accumulate all these quantized values, we obtain this plot over here. So we see for blockwise quantization, on average, the relative error is smaller. How can we further reduce the relative error? Of course, we can further reduce the impact radius of the outliers by reducing the block size, for example, to 4. Again, for the first block, we don't see a difference. And for some arbitrary other block, we see that the relative error is very small compared to the reference of tensor-wise quantization. If we now look again at the accumulated plot, we see that the outlier only affects the other values within the same block. So this is these three other values. All other blocks show a very small relative error. So besides using data types like floating point or logarithmic data types, block quantization is a very effective way to deal with outliers, especially when using integer data types. Previously, I've shown that a logarithmic data type has the smallest relative error across all the data types we discussed today. It's not only of advantage to represent values in the logarithmic domain, but also compute in the logarithmic domain. For example, if you want to multiply a with b, if you do that in the logarithmic domain, this multiplication turns into an addition. So now let's give some examples. Again, we have two vectors a and b of length 128. First, we want to compute the dot product in linear space. We initialize it to be 0. Then we iterate over the pairs of elements in a and b, multiply them and accumulate them on the dot product. Then we do the same computation but in the logarithmic domain. So here we have to compute the logarithm of the elements before we sum them, as depicted in equation 2 above. To accumulate these products, so it's sums in logarithmic domain, but products in linear domain, we have to put the products into the exponent of 2 before accumulating them. So if we now look at the numerical results, they are identical for both implementations. However, the logarithm and 2 to the power of the products is quite complex and costly to implement on hardware. So this is why we are using the Mitchell approximation. This time we will elaborate in detail how we derive these approximations. So when going from linear to logarithmic domain, we have to compute the logarithm of x. And x is a floating point number. So this means we are ending up in this expression. Now we are using a first order Taylor expansion to end up in the expression at the very bottom. Which means that the integer in fraction bit of the logarithmic data type can be set to the exponent and mantissa bits of the floating point data types. This is very easy to implement on hardware and very cheap. A similar methodology applies to the conversion from logarithmic to linear space. So now let's implement these conversions from linear to logarithmic and logarithmic to linear space. And for an exponent of 1, let's visualize the Mitchell approximation. So here we plot the value after conversion to log space against the value in linear space. So we see that we are underestimating when going from linear to logarithmic space and overestimating when we are going from logarithmic to linear space. Of course, these curves look identical for all other exponents. So now let's compute the dot product with this Mitchell approximation. So now we go from linear to logarithmic space with these approximations, sum the pair of elements to get a product, and then we go back to linear space to accumulate all these products. So if we look at the result, now we have a result of 83.95. If we compare it to the previous result, 87.30, we have an relative error of 3.85. Now we are doing this not only for one pair of vectors, but for multiple pairs of vectors. Then we end up in a plot like follows. So here we plot the values of the dot products using logmath with the Mitchell approximation against the standard dot products computed in linear space. We see that we are underestimating the results. Of course, this is a problem and this has to be fixed. However, if we compare the error to the quantization error of LNS8, so a logarithmic data type with 8 bits, we see that the error introduced by the Mitchell approximation is smaller than the quantization error of this logarithmic data type. So this means computing a dot product with Mitchell approximation could be a way to reduce the implementation costs in hardware and the energy consumption when executing and deploying large networks. Now let's go back to the main presentation. Now we are back in the slides. To conclude the talk, let's have a look on which hardware system supports which data type. Please note that only data types with 16 or less bits are listed. In summary, most hardware systems support an 16 and an 8-bit data type. There are only few systems that support 4-bit data types. And only the newest generation of NVIDIA hardware supports microscaling data types. Also note that there is no clear preference for floating point or integer support in this table. However, the newest generation of Google GPU adds a support for floating point 8, which might give an indication. And now let's have a look what is actually the advantage on these hardware systems if lower precision data types are supported. Here on the example of a NVIDIA GPU and Google GPU. So usually if we halve the bit width of the data type, we double the throughput in terms of floating point operation. In summary, Less bits. I've shown how to quantize distributions to low precision data types. Together we characterized different data types, especially in the context of the quantization error, and identified L and S to have the lowest relative error. And we addressed outliers by block quantization. Log math. I've shown how to turn multiplications into additions by computing in log space, and I've introduced a Mitchell approximation for efficient hardware implementation. More compute. Via less bits, I've shown how to reduce the requirements in storage and bandwidth. Via log math, I've shown how to reduce the cost of the computation itself. And overall, we've identified that low precision data types are the most effective way to reduce the energy consumption of neural networks. Enjoy the resources, especially the coding part, and please check out the other talks by Marcus and Timon. Goodbye.